let's prove for simple harmonic motion that the period itself is equal to 2 pi multiplied by the square root of m over k. Simple harmonic motion just simply means that we have a mass which is attached possibly to a spring, and that spring gets compressed or it stretches out. There is no transfer of energy into anything except from the elastic potential energy and kinetic energy of the movement. There's no frictions, no resistances, nothing like that. And what happens is that the mass just bobs back and forth, back and forth. Now, I want to be able to show you this by relating it back to a mass which is circling around. And what we're going to do is we're going to project that particular mass movement, which is going around the circle, into the x-axis, which is going to be the simple harmonic motion. Now, what I mean by that is the following. So here's a simulation, how I'm going to relate two things together, which is the spring force to a centripetal force of masses that are identical, but one is moving in a circle and then the other one is bobbing back and forth. So here's a simulation, which I'm going to play for you, what I'm referring to and what I want you to visualize as I'm doing this. If you have taken anything to do with centripetal acceleration, you know what the force would be. The force is simply the mass multiplied by v, which is the speed squared as you're moving around the circle, divided by the radius. Now, in this case, notice that the radius itself is equivalent to the maximum that you have of the bobbing, and that's the blue mass that you see there, that's bobbing back and forth on the x, and that bobbing would be attached to a spring, and it just goes to the negative, back to the positive, and so on. And if you now take the red ball, which is going around, okay, or the red mass, which is going just around the circle, and you project onto the x-axis that location of that red ball, you notice that it's identical. You notice the line, okay, is moving along so that you can see that. And what we want to be able to do now is to relate the actual spring force, which is the restoring force, and make it equivalent to the centripetal force, but the x component of the centripetal force that we would have. So let's take a look how we can do that. If we take this, then we know that our spring force is equal to negative, which is this is by Hooke's law, k, and k is the coefficient, okay, of the spring itself, and it is multiplying by x, okay, and the x is just the location that you have, or the displacement, sometimes it's just delta x. Now, your centripetal force is equal to the mass times the v squared divided by the radius. Now, we only want to know what the x component is. Now, keep in mind that this right here is just the centripetal acceleration. So that would be the movement of the ball in the x direction, at least for us, okay? Or the actual mass around its circle. Now, let's break this down a little bit further. So if you take a look at this, and I want to just concentrate on the speed itself, what is the speed as we go around a circle? Well, the speed would be equivalent to 2 pi times r, which is the circumference of the entire circle, divided by, well, the period. Now, the period itself, okay, would be just one revolution of that circle. And now, please note that this right here, typically in physics and in other sciences, is known as the angular speed. So this is the constant angular speed, known as omega. So instead of writing it like this, I'm going to write it as omega r, and I'll return to the 2 pi over t, okay, in just a few moments. Now, once I have this, I can certainly plug this back into the equation. So I'm going to get m, and substituting this in, so omega r, so this becomes squared divided by r. And notice that we're going to get m, omega will be squared, and then the r will become squared, but there's another r at the bottom, so one of them will cancel out, and this is what we will have. And that is the centripetal force that we would carry out. Now, the other component that I want you to know is that the r, that would have been on the actual circle itself. So if we had a circle, and so let's say this is our central point right here, and this would have been your radius r. So this is just moving around all the way through as you're going through within here. So that is the mass moving around its circle. And now that mass, of course, okay, will have two components of its location. Sure, it has a radius r, but that radius and now will change what the y value and then what the x value is. And we're interested in the x value. And this is exactly what you're seeing in the simulation. So in the simulation right here, we are noticing that the blue ball is just a projection onto the x-axis that we have. So hopefully that makes sense to you. And of course, this would have been just your, so this is your y. If I project this out in terms of the motion, this is your x right here. And this is what we're referring to. We just want the x component in here. Now, of course, r is nothing else but x squared plus y squared by Pythagorean theorem. So that is your r, and that goes back to elementary school. And since we're only interested in the projection onto the x, then our value that we have has nothing to do with y, because y we're not taking into consideration. We want the acceleration of our actual mass moving in the x component. So therefore, this would just simply be the square root of x squared, which is just x. And now that x can get substituted back in there so that our centripetal force related to our x component would be this. Now, of course, we can do the centripetal component of the y, and then if we added them up together and then brought them back in, then we would get the overall centripetal force. But we're only interested in the restoring force from the spring, which is only in the x. It does not go in the y, so we don't need the y. Well, so now what we have is, we have our restoring force, which was negative kx. Now the negative, remember, if you think back of Hooke's law, that negative was simply to do with the direction, right? Because it was a restoring force. So we want to know what the magnitude of it is. Well, the magnitude of this restoring force is just kx. And then, of course, we also just want to know what the magnitude of the centripetal ones, because we obviously know that the centripetal force is always towards the center of the circle. So technically, we're only interested in this. Now, if we equate these two, these have to be equivalent within here. So if these are equivalent to each other, then what you will notice is you will have that your x component will fall off, and you will obtain, and I will put the omega squared is equal to, now this is going to be nothing else but simply k over m, as we have it right there, so it's just dividing by m on both sides. And now that implies that omega is equal to the square root of k over m. Well, so this looks very familiar now. Now, omega itself, we just mentioned, is 2 pi over t. This is just by definition. So what we would have is that 2 pi over t is equal to k over m. Well, we are done here. Now, we can take the reciprocals of both sides because we want the t on top. So t over 2 pi, and if you flip this side, you have to flip the other side as well. So this is going to become m over k. And now, as you can see, the period is going to be 2 pi multiplied by m over k in this way. And that proves, by comparing it to uniform circular motion, what the period would be. And notice, of course, that the period for both is identical. So as you can see there, the actual circular motion is identical as you're going through. So there you go. You have now proved it. Hopefully you found this video useful. We'll see you in a future one. Bye, everybody.